time to start. This way, the sooner we can get out of here. I was looking at the syllabus. Don't forget the midterm is the 19th of October. That will come up in a few weeks. We'll actually have a review beforehand on the 17th of that. But just a word to the wise, you know, it's going to catch you. All right. We're now going to talk interpolating polynomials. We're into our 10th lecture already, the 5th week. Time flies. All right, interpolating polynomials. You're basically going to estimate or determine values between some data points. You've actually done this probably by hand. When you look at tables of data, the backup thermodynamics books, or whatever, where you're saying, gee, what's the value for this condition at this particular time or place or whatever. So anyway, it's extracting information from data. And generally, the data point that you want isn't there, so you got to figure out how to get it. All right, if you have n plus 1 data points, there's one and only one polynomial of order n that passes through all the points. That makes sense. There's a variety of mathematical formats. There are two that I want you to be aware of. One is the Newton, and the other is Lagrange. We'll actually go over both of those. All right. The most common one is Lagrange. All right. Although you may find a lot of codes and so forth that are using the Newton method. All right. Linear interpolation, connection of 2 points with a straight line. If you can't do this, we probably are remiss in your education, going back to about 2nd grade or something like that. I think you were doing straight lines even that format, maybe even kindergarten, I'm not sure. Excuse me. Okay. Easily visualize using the formula f1 of x denotes the first order. All right. What does this look like? Does this look familiar to you? Yeah. f1x equal f0x plus. Already plus. Where does this come from? It starts with a T. Taylor series. Told you it's going to come back. Yeah. All right. This is what happens if you were to graphically interpolate or try to come up with a linear interpolation in this sense of a curve. Here's the curve, right? And so you're, in essence, picking 2 points, endpoints on this, and you're saying, gee, what would this value be somewhere in the middle of that point? All right, now, what's the good side and the bad side of this is what?
It can be inaccurate.
It can be very inaccurate, right? If this is the true nature of the solution, and you're coming up with a linear approximation, you're missing a lot of information, obviously, from here. What would you do to improve this?
Take smaller intervals.
Well, you could, but what else?
Use the second one.
Yeah. You go up. You go up in order. You go to a 2nd order, or 3rd order, or whatever. All right, examples of interpolating polynomials. Obviously, a 1st order approximation. This would be what?
2nd order.
2nd order, or a quadratic, right? Quadratic, the minimum polynomial you can use to capture curvature. All right, what's this one? Cubic. What's this called? An inflection, right? So anytime you hear inflection, you're going, ah, they're probably inferring a cubic, a curve that's going to go from one way, basically one direction to another. All right. Okay, the Newton. Here's the term, all right? This is a difference, all right? That's a finite divided difference. You do that all the time. Probably didn't know it was attributed to Newton. Right? So you're taking 2 values, you're dividing by the distance between the 2 values or whatever that would be. That's the finite divided difference. All right, obviously as the interval decreases, the continuous function will be better approximated by a straight line. Why is that? Because of Taylor series. Taylor series says delta x. As delta x shrinks to 0, you get the exact value, right? So what we're doing is approximating here. So it depends on what we're going to use, obviously, is intervals. All right, find the natural log of 2 using linear interpolation between log 1 equals 0 and log 6, 1.79. Then do it between log 1 and log 4. Okay, here's what's log 4. So if I use big difference, right, value between 6 and 1, I get 0.358 whatever. If I use it over 1 to 4, I get 0.46. The real value, or the actual value, is 0.693. All right? Pretty obvious. So what we want to do, maybe shrink down, get as close to the value we want as far as the interval about the point in question. Here's what's going on. All right, so here would be the first approximation, second approximation, here's the true value. So what I'm trying to do is, if I had a value here and a value here, right, I'd probably be pretty close. Okay, quadratic interpolation permits curvature, as we've said before, estimating the connection between points. Now we have a formula for parabola. So let's take a look at this formula. So here's f of 2 of x, it's a of 0, a1x, a2x squared, so forth, so on, so right? We kept carrying out the series. All right? I can do this in terms of the differences. All right, that's what these are. All right, so here would be, if I stopped it right here, just these values, that would be a linear approximation, right? So if I'm going to add one more term, now it sets out here, right? We know that that's a squared term, right? So I'm doing a quadratic. All right. Now I can define these coefficients from this original equation so that they look like this. This is just a manipulation of this equation back into this original equation for the quadratic. All right, so basically I can say, well, let this coefficient be f of x of 0, b1 would then be this first difference, right? Here would be this term associated with that expression, right? This, by the way, is a very important term that you will use later in solving partial differential equations, particularly when you have unequal spacing between data. Right, like a delta x or a delta y or whatever, and you're saying, gee, it's not uniform. I can't use the same delta x or delta y in all these expressions because it's constantly changing. The formula that you use to account for that changing is actually that term right there. All right, let's find log 2 now using our quadratic expression between 1, 4, and 6. So x0 is 1, f of x0 is 0. All right, so we plug in these values. So we evaluate these functions. Right? Now let's determine what these coefficients are. b0 is 0, b1.46, b2. Plug into the little formula that you saw on the slide, you get minus 0.05. All right, f2x can now be solved. Now you have to include all the terms, right? So we're looking x minus 1, x minus 1, x minus 4. Right? Do you see the pattern? Do you see what's going on here? All right. Which yields for x equal to 2, f of 2 is 0.56. Remember what we got before from the simple difference, right? 0.46. Now, that's improved significantly with just one more step that's added. All right, now let's take a look what's going on here. So here's true solution, here's the value. So what I'm doing now is picking up the quadratic estimate versus the linear estimate. All right, so you can see we're approaching true value. All right, so here's the general form of Newton's interpolating polynomial. So B1 is f of x of 1, right? B2, what does this mean when I see things like this? That's supposed to be a dot, dot, dot. What does it mean when these things are written? And in fact, it's probably in your textbook, it's written like that. Be sure to go back to the little formula that is used to define B2, B3, B4, all right? You can see the pattern there. And that's what that means. That's just an abbreviation that says, oh, I understand what's going on. This is what's happening, right? Simple difference right there. If I have 3 terms, or however many terms it would be like this. All right, so I'd have another term, another term, another term, depending on how far out I am in the series. right? Understand? That means dot, 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 down. Okay. This is what's happening. So this is a graphical depiction of what we mean with regards to the recursive nature of the process, what's really happening. So here's f of x of 1, right? If I use that and that value, I get to this value. If I'm doing this, I would use that. If I'm using these two, I go to that. Now, if I want to refine again, I would have that value and that value. Now I have 3 terms, right? And so forth. And I can keep going on and on and on. Depends on whenever I want to stop this thing. Right? Okay, let's look at a third order polynomial. Again, finding the log of 2. This is what the third order expression would look like. So let's take a peek. So here is the linear, the quadratic, the cubic, our third order. All right? So if I gave you on an exam, write the expression for a fourth order, what would you do? All you do is just add one more term, but now it would be
X minus X.
you'd have another difference that would be in there. All right? So that's the pattern. Okay? So these would be the differences then. So f of x of 2, between 2 and 1, is just a simple difference, right? Between 3 and 2, simple difference. And dot, 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 dot. All right? Now I go to the next step, right? So I would get that minus that divided by between 6 and 1 minus 0.0518, whatever. Right? See, that's the process that's going on. Once you see it, it's a pretty interesting pattern and one that's repetitive. So here's how we start. F of x of 1, 0. First difference, 0.46. Remember, if we go to a second difference, minus 0.05. If I do a third term, right, third order, that would be the value. And I step through these intervals, right? So now I plug in, so here's what it would look like. You're actually working this out on an exam, for example. Here are the values, right? So I just plug them in, so I've got this equation, right? Now I solve for x, right? Whatever the value is I'm looking for, log 2. Remember the value 2, plug it in. What do I get? 0.628. Okay, so by going to a third order approximation, I've zeroed in on the answer. All right, let's take a look. Now we're using cubic, right? So linear, quadratic, and cubic. And what has the cubic done? Right? It's moved even closer to the true value. Right? That's understandable because the Taylor series approximation tells us that if delta x, or whatever that difference would be, 0, I would have the exact value, right? But it's not because I'm approximating. So whatever that approximation is, right? I can keep it small or I can add more terms to the expression. And when I do so, it gets me closer and closer to the true shape or the true solution. All right, if you need an M file for doing Newton interpolation, here's an M file. It's not very long. I think if you want to play with it or try it, go ahead, give it a shot. That was Newton. Now let's talk about Lagrange. All right, those are the two interpolation schemes I really want you to remember. All right. Now Lagrange. You start by approximating a straight line. F of x is L1 fx1 plus L2 fx2. Now here's the trick. Right? That coefficient L1 is the difference between x and x2, and x1 minus x2, right? Difference between x1 and x2. This one, L2, x minus x1 divided by x2 minus x1, right? So you plug this into the expression right here. That's what you get, right? Likewise, f2 of x, if I wanted to go higher, right, what would I do? Here's this expression,
Here's,
this expression,
here's,
this expression. See the pattern if I had more points involved? That can be expressed in this recursion expression right here. All right, summation. Right? That would be L1, L2, L3, L4, whatever it is, as far as the number of points that I'm dealing with. So L of I x times F of x of I. That L, when you talk about these divided differences, that's the term you use, right? Mathematicians like to do that, right? So that means, I'm going to sum all these differences setting up in here, whatever that J would be, right? So you can get more and more terms. Okay. Let's see what's happening here. I have L1, L2. Remember, the sum of all the L's is equal to 1. Right? And in fact, this is a very important principle in finite element methods when we talk about the elements, whether they're linear, quadratic, cubics, or whatever. And these L's, actually, we refer to them as shape functions. Right? So here, we're talking about L1, L2. All right? So what's going on is the combination of these things give us the value. So if I want to know what's the value sitting right here, it would be that part of L1, that part of L2. Let's keep it really, really simple. Maybe I can sketch it out for you. They're always missing. If I want to know what the value is at fx1, what's the value of L1? What's the value of L2?
L2 is 0 and L1 is whatever L1 is right there. So it's
Correct.
just L1.
All right. What would be the value at f of x2 for L1, L2?
L2.
And L1 is what?
0.
All right. So what would it be if I were right in the middle? Half, right? Half of L1 or half of L2, right? So remember, the combination of the L's is always 1. Okay, let's find L2 using Lagrange interpolation for first and second order. So here are the values that I have on the list, right? 3 values. So here's what the function would be at those 3 values. First order polynomial. So what I'm after is the value of 2 setting somewhere in there, right? So I go, okay, what is it? I plug it in to here. I get 0.462, all right, for F1. Now, F2, I plug in. Now, notice now that I've gone a little higher, right? So I've got these distances, right? So I'm going this and this. Here was the first, right? Here is that and that, 46. All right? So I now get 0.565. Get the idea? All right, if you want to know what a pseudo, remember we talked about pseudocode before? This would be Newton's dividing difference. Create a substitute, whatever you want to call it, Newton. This is, see these do fors? What are the do fors and the indus? What does it mean? Loops. These are loops. So these are steps that the computer is doing over and over again. Now, this is called a nested do loop. Why is it called a nested do loop? See that? It's got a loop inside a loop. Now, remember, computers pretty stupid. What's the computer going to do first?
First 2.
Whatever you tell it. Which one?
First
Going to do the outer loop or the inner loop?
It's going to see the outer loop, but then it's going to go to the inner loop and finish the inner loop before it goes back to the outer loop.
Exactly. When you have nested do loops on this, even in your M files or your MathCAD or whatever, it'll do the inner loop first and work its way out. All right? So sometimes if you're programming, you're going to what's happening here, you might have a loop that's messed up or your indices are backwards or whatever. Okay? But this gives you kind of an idea of what's going on in kind of pseudo recursion form. And then from that, you can say, oh, if I wanted to write a code, I know what I have to do here to get this thing to work. All right, there's an M file to implement Lagrange interpolation. All right, what do you notice about this versus the new M file? This one's shorter. A lot shorter. Okay. So that's the code setting right there. Pretty simple. And you'll find that, particularly with MathCAD, it's got a lot of nice internal calls that you can capitalize on, so you don't have to rewrite a lot of code and so forth to do that. It just makes a call. But I want you to know, when you make that call, what is it that it's doing?
MathCAD or MATLAB, sir?
Yeah. Well, MathCAD, MATLAB,
Oh, okay.
right? Even Maple. All of those packages now have a lot of these things built. Okay, Lagrange interpolation. Calculate the density of air at 1 atmosphere pressure at a temperature of 15 degrees C based on these 4 values. So you got a table of values that you get from the lab. All right, so you've got to out and measure these things. But you want to know what's the density of air at 1 atmosphere, temperature at 15. So you're saying, well, okay, I want to know what the value is in there. All right, this is what you would do as far as a MATLAB code. Okay, what's that mean?
Gives it 16 decimal places.
Yeah, look at the answer. Right? Give me a long formula. I want to know just how accurate it is. Here is the table values here, temperature. Here is the density, setting right there. Density equal Lagrange, TD 15. That's what I want to know. 15. Oh, there it is. All right.
TD 15.
Not hard. Okay, now let's talk about extrapolation and oscillation. Extrapolation, I think everybody knows what that is. Estimating a value of f of x lies outside the range of the known base points. All right, let's be careful here. Higher order polynomials can be very ill-conditioned. Why is that? They're sensitive to round-off errors. Avoid if possible. Right? Lower order can be just as effective in capturing curving trends. That's what I'm saying. You never want to use anything more than you have to as far as the order, because you could be wasting cycles. The round off can get. I'll show you an example here in just a minute. Okay. Extrapolation of data from a curve that fit existing data nicely. Test case is probably by Carl Runge, 1901. I'm going to show you this Carl Runge thing. You'll see exactly what we mean by what looks proper versus, gee, I did this right as far as a polynomial interpolation, but that's not even close to what the real effect is. Okay. Possible divergence of an extrapolation. So here is the true curve, all right? And so you've got 3 points. So you're going to say, oh, well, I'll just use the 3-point polynomial on this, and then I'm going to extrapolate out as to what I think the next value will be. Anybody do forecasting on the stock market? You do? Are you successful?
Stocks and everything. You can buy what you need.
All right, so if you extrapolate out here, you'd go, well, I think we probably ought to sell the stock down here or something, maybe. In actuality, it could be going up. Right? So that's the problem that you face here. So you have to be careful. All right, now take a look. Here's a 7th order polynomial. Make a prediction of the U.S. population in 2000 using data from 1920 through 1990. So here are the data points. So you go, I'll use a 7th order polynomial. Man, I'm going to have this thing down. That's pretty accurate, right? Right out there. So you make a forecast. You go, I guess we're either going to have a serious flu epidemic or there's a war or something. So now you're putting on your practical hat and you're going to say, do I believe this? Right? What do you think it's going to do? I would say it's going to go that way. It's definitely not going to go that way. So here's Runge's function. Here's what happened. So you've got these data points setting right here. So using Runge's function, the dashed lines, 4th order polynomial 55 points, right? So here's the exact solution to the 2nd order equation. Here's what he got. All right? So if you're running polynomial here, you want to fit it through all the points. you wind up with something that looks like this. Now, what do you think is more true to nature as to what's going on? I would bank on the dotted line, right? These are like spikes that you see in data that you go, oh, here's probably the trend, but here's a spike. But if I did it this way, it looks like it's oscillatory.
Would reducing the order of the fit make it more accurate?
Sometimes, that's what you can do. All right? Here is a rungus function compared to a 10th order. So you thought, well, 7th wasn't, or 5th, or whatever. Let's bump it up. Let's add a lot more. Now, obviously, we're doing a good job of capturing what's going on in here, right? But look what happened on either end. And if you said, I want to know what's the spike or what's the high value here, what would happen? You'd wind up picking the value there or there, right? And in truth, it's really there, right? And it's because that polynomial is going to fit a curve through every one of those points, one way or the other. So this is why sometimes you've got to balance this by saying, that's not even close. I know it's not oscillatory. Okay, now, what I want you to do, continue reading the chapter on interpolation. Right? Now, next week, we're going to talk about cubic splines. Right? Also, your homework is due next week. How are you doing on the homework?
Pretty slow.
Anybody complete the first problem? Did you get a reasonable answer? Okay. Who else got a solution? Right? Okay. You comfortable with the solution? Makes sense? Okay. How about the second problem? The circuit.
I sort of did my own. I did it solve for the current,
Yeah.
and then just forward back in. So I'm gonna redo it.
Okay. Now you guys are using MATLAB?
Yeah.
Okay. All right. So everybody, no problem about setting up the equations on the first problem, or the second one for that matter. You're comfortable with that, you're getting a solution, fine. A couple of things to remember. I think I've said this before. You can have the right equations and you're programming incorrectly. And so sometimes you get caught up saying, is my math right or is it the program that's causing me fits? And of course, vice versa there. So welcome to the world of computer programming and assessment and analysis. Sometimes you don't know which it is, and it can be very, very frustrating and time consuming. That's why codes can become very, very valuable. You put a lot of time and effort into these things. Are you sure you want to just hand it over and give it away then, after you've done all the work? That's one reason why commercial codes are so expensive. They're really popular, like CFD codes. You know, they'll go anywhere from $25,000 to $50,000 a copy. And that's because there's a lot of manpower and effort that went into those things to make them work. Okay, any other questions? Right now, next Tuesday, I won't be here, but Shaling will. And Shaling is going to give the lecture. So one of you guys, I want you to tape it so we can archive it. And she's going to take roll, so remember, if it drops below 50%, shut.
I got all kinds of angles.